So we'll start off with a panel discussion about nuclear science and technology. So as you might know, there are many more applications there of nuclear science um, that range from things like healthcare to energy. And it's steering medical breakthroughs and fostering sustainable solutions for industries. So this panel will talk about both of those things and how it's making industrial processes more efficient, as well as its influence on healthcare and its outcomes. So the panel will be, on the panel we have M Krishnamurthy, who's the Center Director at TIFR Hyderabad, and Smitha Manohar, who's at BARC Mumbai. The panel will be moderated by Aditi Tandon. She's a journalist and a fact-checking trainer. She's currently a senior editor at Mongabay, India, and writes on environmental science. So over to you, Aditi.
Okay, good morning, everyone. It's so nice to see all of you have taken time out today to participate in this session. And I'm sure we're going to learn a lot of new things about the fascinating world of nuclear science. With me today, I have Smitha Manohar, ma'am. She is from the director of the Nuclear Recycle Group at BARC, and outstanding scientist for more than 36 years. She's responsible for developing and deploying for the back end of nuclear fuel cycle. And we have Mr. M Krishnamurthy. He's the center director at TIFR Hyderabad. He's been a faculty member in TIFR in Hyderabad since 1998, and he's been one of the core people setting it up in Hyderabad. And one of his main areas of research is intense laser physics, where you use high-powered lasers in non-conventional sense. And they will talk more about their work for you to learn from, for you to know what are the amazing things that are happening in this field in India, in our neighborhood, and how we're contributing to the global progress of nuclear science. For this talk specifically, we'll talk about industry and healthcare. And Smitha ma'am, I'd like to start with you about how does nuclear science contribute to the advancements in industrial process? What are the application in industries? If you could talk a bit about that.
First and foremost, thank you so much for giving me this opportunity of being here with all of you young people. It's an awesome, environment, and it makes me very happy to be here. And coming to your question, Aditi, nuclear always what comes to mind for most of us, and it is rightfully so, is that it is the energy, nuclear energy, or the other things of nuclear. But there are so many other industrial uses of energy which we use in our lives every day. We use nuclear, but we cannot fathom that these things have come from nuclear. For example, if you look at even agriculture, we feel there is nothing to do with nuclear. However, in agriculture also, when you want to make new varieties of rice, or beans, or groundnuts, then you play around with the DNA, right? And to play around with the DNA, to tinkle with it, you have other sources, and you have also radiation. And so with nuclear is a definite distinct advantage to get us crops which are resistant to diseases, crops which are small. This is one. Second thing, healthcare, which is very evident, because all of us know how it either therapeutic application or for a diagnostic application. For both application, radioisotopes are very much used. Third is in water. When the streams of water needs to be seen, which side it will flow, what it has to do, a simple small radioisotope is put, we start looking at where the tracer has gone, and then if we can advise the people, okay, make the canals like this, make the thing like that. So from a small stream, you will have gurgling rivers, beautiful green rivers everywhere. So these are some of the applications which come into my mind, which can spark your minds. Thank you so much. Yeah.
Thank you. And so if you would also like to add on some of the industrial applications of the work you're doing.
First of all, thank you very much for inviting me here, and thank you all for sparing your weekend to come and listen to us. Um, when we talk about nuclear and nuclear science, um, nuclear power is one thing, nuclear science and applications of this methodology. So at the core of this science is to be able to accelerate particles which can cross and reach the nucleus to do whatever we want it to do. So there is this physics of or technology or methodology of accelerating particles that is very important. And then once the science happens, what comes out and how we can use it. So there are all the three aspects. And I must first acknowledge that the Department of Atomic Energy and the Government of India has been extremely sort of reaching out to these needs and to support this science to the best of the possibilities, because this is not something that you can switch on. This is not something that you can buy. We have to make it, whatever we can do it ourselves. So there are three layers to it. I will only talk about the layer which is related to the nuclear science or acceleration of particles. Tata Institute of Fundamental Research is one of the fundamental research institutes which have been doing this kind of science for a very long time. And we are interested in the physics of the problem or the science of the problem. And that requires, as the technology changes, things change quite dramatically. So any of you who have gone to Bombay, even from the Marine Drive, you would see a very, very long building, which is one of the first accelerators or one of the prime accelerators that was set up to do nuclear science. But the technology keeps changing and methodologies keep changing. And I'm interested in a research where we use ultra-fast, high-intensity lasers to actually shrink this whole thing into a very, very different, using completely different methodology. So our aim in some sense is to take a kilometer-long accelerator and bring it down to a few millimeters so that it becomes compact, it becomes deployable for medical or other industrial applications. And the science of it, we are not at a stage to deploy many of these technologies, but in the next decade or so, many of these are going to be completely irrelevant, and we are doing the science of that. Thank you.
That's amazing. I mean, I'm sure it's inspiring for all of us, especially those who are interested in science, those who are studying science, to know where this research is taking us. And we can talk a little bit about the healthcare industry now. What are the applications of nuclear science in healthcare? And what are the developments you're seeing? Like some of it is still being researched, some of it, is already applied. So if I could start with you to give some insight, and then we can talk more. Yeah.
Broadly, you can divide it into diagnostic and therapeutic application. So if you look at, and now the prevalence of either heart diseases or cancer, these are very much on the rise everywhere globally. And if you see, these radioisotopes have a very big role to play. For example, you have technetium-99 M, which is a radioisotope which is used all the time for diagnostic application in a very large manner. Now, talking about this, talking about copper-64, talking about lutetium, you have so many radionuclides which can do so many. Now, from where are these radionuclides coming is the question to ask. So, for people who are younger, older generation people will know, for young school children, I want to tell these radionuclides, most of them you have two ways of producing. One is you can produce in a nuclear reactor. You take the main material, irradiate in the nuclear reactor, then you will get the isotope, take it out, and then separate it chemically to give you the purer form of radioisotope, which you can use for healthcare. Another way of producing this radioisotope is what Sir just now mentioned, Krishnamurthy Saab, that when you have an accelerator, in an accelerator-driven system, you can have medical liniacs and things like that, where you can also produce this medical isotopes. Now, what are the requirements for medical isotope? When something has to be injected into your body, that radioisotope, you have to connect with some other organic molecule, like dotatate, like other things, then only then only our body will accept that. Without that, if you simply give one radioisotope inside, no, body will not accept. So you need to also research on what organic molecule you are going to bind along with the radioisotope, and then when you put it into the body, it will reach the correct cancer cell wherever you want and do its application. Another one I will tell you, you look at cobalt-60. Now this is a strong source of gamma. Now, gamma is normally given from outside. When you have cancer and cancer therapy, one of them is gamma dose, which is to be given. There, some protocols will be designed, and in a very narrow manner, only to that organ, they will expose it to an amount of radiation, which is calculated by the radiation therapist and the doctor together. Now, this sort of a thing, again cobalt-60, from where cobalt-60 is coming? Cobalt-60 is again getting irradiated in a reactor. These all I finished from reactor. Now, I will tell you something which India is also doing, other countries may be also doing. Now, what we are trying to do from radioactive waste, we are trying to recover a few radionuclides which are for societal application. For example, cesium-137. Cesium-137 is again a gamma emitter, okay? And why cesium-137? Because cesium-137 is 30 years half-life. Cobalt is 5 years half-life. So if you could populate your irradiator with cesium-137, it will not come back for replenishment very fast. Once done, done. And to make cobalt-60, you need neutrons. Neutrons are a resource for us in the reactor. If I'm eating away one neutron, I don't have neutron to carry out the next fission. Okay? So chain reaction, I'm eating away neutron, it is a resource for us. So, whereas cesium-137, it is coming from waste. So, right now, India, we are making it to glass pencil. We are vitrifying this, what cesium we remove from waste. We are making it to glass pencil, and we are putting it into blood irradiator. About 20 such irradiators we have already populated. And so, we are, furthering. This is again in the realms of development, R&D and deployment, and this is one. Another one I will tell you is very rare, recently which we have done is ruthenium-106. Ruthenium-106 again is a beta emitter. And this beta emitter, when you can take it out of the waste and put it into silver plaque, and you can put it in the eye, there is eye cancer treatment, no? There are a lot of patients in India who have eye cancer. Now this, if ruthenium-106 plaque, it is sandwiched in silver plate, and we call it the ruthenium brachytherapy source. That if the doctors will put into the eye, give for 1 day or something, remove it, and the cancer is treated. So these are some of the very good. Another one is strontium-90. So strontium-90 gives yttrium-90. Yttrium-90 is used for again cancer treatment. So again yttrium-90, you have two sources. One is from the reactor and one is also from the waste. So we are also taking it out of the waste, small amount. Every week we give it to RMC, and RMC patients are getting that as a combination with lutetium. Lutetium-177, they will give it in combination. And again, these are all in, we have to develop it further. I'm not telling we have done too much, but these are all in R&D domain. And as we take this forward, it will be the benefit of public at large. Yeah. But one thing I want to tell, ruthenium-106, which BRC makes, we are giving it only less than 50,000 rupees one plaque, whereas till last year, when we imported it, we were importing it at 10 lakh rupees one plaque. So this is the nuclear advantage which India has. Thank you.
Great.
Just add one point to what ma'am has already said. You want some of these isotopes as a marker for you to see what is going on inside the body. Now, if it stays for too long, emitting this radiation, it will be very harmful to the body. So you need to have something that dies very, very fast inside the body, which means it has a what we call as a small half-life, which means it has to be made right next to the patient, sometimes right next to the medical hospital, and it has to be used immediately. Now, as you can imagine, if this is an isotope that has to be made in Bombay and has to be sent to somewhere in the far end of other end of India, you can imagine, even to take a flight, you may have to change 2 flights or 3 flights, and by the time you reach, how much sample you have, so which means you'll have to make a lot more. So these are things that has to be made almost by the bedside, for a proper best use of it. So we can't buy it from anybody else because we can't, how much money ever we have, we can't buy these things because by the time they come from a foreign country, their efficacy would have been lost. So while there are lots of things that are being made, there is a lot more that needs to be done because the modern India is not going to be, should not be limited to metropolis or to the 2-tier, 3-tier cities. These kind of facilities have to reach everywhere, which means we need a lot more capacity building about these technologies, and then also find new methods of making compact, making more efficient systems. And we have the manpower to be able to do this. And in my opinion, personal opinion, we need a huge industry government participation because it is then it can actually take off in a completely different manner. That is very, very important.
Great. And so I'm hearing that there is, there are probably challenges with other technologies that nuclear science and nuclear technology can overcome. But what are some of the challenges within the research itself or the science, or to make it applicable for everyday use? What are some of the challenges you faced? And like you said, you need a bigger industrial push, a bigger policy push. If you could just elaborate about some of the challenges both of you face in your field of research. Yeah.
So for example, as a scientist or a physicist, most of us play with instruments that are, we are toying with them to improve something. But, so there are some things that are at a conceptual level, some things that are at a deployable level, something that have to go to industrial level. Now, unfortunately, the amount of participation of the industry at levels where it is not viable for commercial switch on is seriously wanting. And I think for a vibrant society like India, and the economy that we want to, economic status that we want to reach, there is a huge need of resources, both human and money. I would say human much more than money because, well, we can make cut with software only to a certain extent. We need also to take hardware development and hardware thing as the aspect to do, and that I think we need a lot more joining hands.
Maybe I can add on to that is I feel we also need to, public perception also has to really change, because even recently 10 days back I got a question whether if we irradiate something will it become poisonous or something will happen. So this thing, for example, I will tell you something. This mangoes, India used to, even now we export mangoes to US. Okay. Now, US will not take mangoes from India unless it is irradiated. There's a protocol. Why they want to do is that they don't want Indian microbes and Indian things to come into their land. Same way for us. We also don't want other countries' microbes and all to come into India. So you see, internationally, it is well endorsed that you need to irradiate these mangoes. Now, last year, after this protocol has been established, we are sending mangoes by ship, not by plane. Before, we were sending by plane. Now, with irradiation, because we know it will not ripen that early, we are able to send it by ship. And when it is going by ship, the advantage is that the cost of mangoes, which they are selling in America, is coming down. So you see how everything works together. But only thing you have to allay that fear. See, onions. Now, you all know, Lasangao has one irradiator where we are irradiating all this. Now, the thing is, it is very difficult to explain. What I'm going to say is, we have to go around and tell people that it is not, there is no detrimental thing. In fact, it is much better than putting chemical and doing, for example, other fruits and all. Chemically, instead of doing this irradiation application is very good. It is not harmful at all because it goes through a proper protocol, proper check, proper R&D. Then only it comes to a level that we know, okay, this much is good. So that type of thing is also to be, and at the same time, all these facilities also have to increase in numbers. We have very less numbers now. And from our side, we have to work with, in fact, for that, I think Government of India is also allowing us now public-private partnership. In that mode also, we want to bring this up. Lot of private irradiators are also coming up. So with that, definitely a lot of benefits will reach the masses. Thank you.
Great. So, yeah, hopefully in the coming years, we see much more investment on the research side and on the, before it reaches the application stage, which is what everyone looks at, but more about, the work that goes on behind the scenes before it reaches that. So my next question is on the, when we talk about nuclear power specifically, there is a concern on the security aspect, the safety aspect, and much of this gets talked about probably more than the application. So I'd like you to just address that, like how can we ensure, that the work we're doing is addressing these concerns and we're using nuclear science in a more responsible way and definitely in a way to better society. Yeah.
Thank you. That's a nice question. Actually, now this gives me an opportunity to tell all of you that in India, we have uranium sources less and thorium sources very large. If you see the Kerala beaches, we have lot of thoria, but uranium is not that much. But right now, uranium so if you see the three-stage policy of what was envisioned by Dr. Bhabha himself, that how we have to go through that thing, that is, because of that, we have PHWRs. Our mainstay is pressurized heavy water reactors. And these are like the Canadian reactors, but now these completely indigenized, we call it Indian PHWRs. And so this has got heavy water, pressurized heavy water reactors. So these heavy water reactors need this thing. And these, if you look at the safety, from the safety perspective, these are one of the most safe reactors internationally endorsed also. But only one thing I should say here, this is 7,000 megawatt day per ton. But why we went for this? We went for this because we had ample natural uranium, and so we are going ahead. But also multitude of other reactors, including LWRs and now forthcoming fast breeder reactors are all coming into play because we want to reach that other end where we want to utilize thoria. But that again is futuristic. Right now we have done small level work only, but each step adds to it, and hopefully one day we will reach where we can, because in fast reactor, thorium utilization becomes much more simple and easy. So that is our roadmap, that we want to go through the fast reactor and go to a place where we can use the vast abundance of thorium which we have in our country. And then nuclear will be very, very useful for us. Yeah, thank you.
I'm not really a nuclear power expert, so whatever I'm saying is not from that core expertise. But every methodology has certain rigor by which it is done before it becomes a deployable activity. And from whatever I have seen, we have very, very good standards that are set up. Of course, there are a couple of incidents that happened in the world because of which all of us get very alarmed. But, there is also safety network that is built in. So I think the perspective that, nuclear means danger, nuclear means this one, has to be sort of come out of that, because there are methodologies by which very, very good many things are in place. The technologies have improved, the way things are handled and the way things are made, compactified, has improved a lot. So it's not that dangerous, and things are changing very, very fast as we put in more and more research and more efforts into it. So for example, one of the, though we are never anywhere close to the nuclear power from the laser-produced plasmas, but there is a huge program happening in the Western world where they have put in billions of dollars, because instead of a fission, you go for a fusion technology. Yeah. And that is a much more safe thing, because the moment you switch off the lasers, things are off. And of course, they are not at the stage at which they can produce power, but these are the things that are going to come as we progress more in science and more in technology. And I don't know how many of our own people are aware, there is this a strong program that India is very much party to the thing called International Tokamak Energy Reactor. So this is a completely fusion-based reactor, which hopefully at some point of time will be the giant solver for when many things are exhausted, whether it is all the known technologies that we know and all the problems that will create in making some of these technologies. Because every technology has also a problem. If solar, you may talk about it, there are enough problems with solar as well. And when you franchise it to large perspective, there are associated problems with it. So every problem has a solution. Every solution has to be worked out.
That's a nice way to put it. And I think as someone who writes on science, especially environmental science, there's something that we always try and communicate to the people is that science is always evolving. There is a lot of research that continues happening. So what you know today may change tomorrow. Technologies of today, which you may think are not the best, may not have the security, it may change tomorrow because there's constant work towards improving and developing all these technologies. So in that sense, if I could ask you, where do you see the use of nuclear science going ahead in industry, in healthcare? And we have a lot of young people here, we have school students. How can they, just improve their knowledge of it or participate in where, this kind of research is going?
Yeah, thank you. Actually, yes, this is a ever-widening field for research. So, like she rightly said, what is for today may not be for tomorrow. And like Sir also pointed out, who knows, a few years from now, you don't need the radionuclides and straight away the particles will help us to do the job for us. So, it's magic, it's sheer magic. And all of us, see, I believe in one thing, everything comes, but first that idea has to come into a human mind, no. That mind has to be ignited, that once that first this thing of idea comes, and then you put passion into that, and you start working towards that, it builds momentum, and once it builds momentum, it will become reality one day or the other. This is my humble this thing. So from this perspective, I say each person has his or her role to play, be it nuclear, be it non-nuclear. Science is everywhere. And what is nuclear after all? Nuclear is what is inside the nucleus. That's all, no? What is outside the thing is we don't call nucleus. But atom consists of nucleus as well as all the electrons moving around. And that's all it is. And you put all these atoms together, you have molecule. Molecule, you have substance. Substance, you have gas, liquid, solid, all that comes. What I am trying to tell, once you start working, no, children, there is nothing like science, there is nothing like engineering, there is only interlinkages. To perform at that level, to get something big, you have to have these interlinkages. The more you see it as one whole, you see one big picture coming into that thing, then you will see automatically things starts falling in place. And things will progress like that. So in this, just before the thing we were talking, and so many things came out. So I think in the same way nuclear also, it's got a very big role to play. Like Sir pointed out, in the middle, if you want enough of power, now I can say that even throughout the world, no, thinking has again changed. You will see, you will read in the newspapers, no, nuclear renaissance is now on. Before even because of Fukushima and because of 3 Mile, which happened long time back, all this fear, but finally when they put it all in writing and they start doing the balancing, they realize there is no option but to go for nuclear. And so nuclear is a definite advantage. So only thing like even when cooker came into existence, when I was born in the year 64 probably, cooker was seen like that only, like an accident, it will make an accident. But once you learn to use it, then it is so easy. Today you cannot think of life without LPG gas or cooker, or no kitchen is without that. So it is something like that, and all of you have a role to play. Be it only the scientific temperament and that scientific outlook has to be developed in every child in this country. And I'm so happy to be here that, this fast is trying to do that. And once we do that, no, everybody will have a role to play, and it's a huge process. It will continue. Thank you.
So, I just add to, she used the word magic, all right? And I'll just give you an example of that. Again, if you go to the the beaches in Bombay, not Marine Drive beach, and from there you can see an accelerator. Again, as I said, it's an iconic building. It's a 10-storied building, and that produces 10 megavolt proton acceleration. Today, there is demonstrated work in India and everywhere else that you can shrink it down to 2 millimeters or less. 10 years ago, this breakthrough came saying that we can reduce this down to 1 or 2 millimeter. Today, we are talking about a GeV electron acceleration on a centimeter scale. Now, just to give you a perspective, the Stanford Linear Accelerator has a 5-kilometer acceleration column to be able to get to 10 GeV. Now, we are talking about that GeV accelerator being shrunk down to a podium of this size and an acceleration column that is 1 centimeter. So the science is advancing very, very dramatically. And for my sort of appeal to the young people is, there are avenues which give you money. There are avenues which will make you part of the magic. It's your choice. It's not that, being a scientist deprives you of the basics. It gives you very, very good basics. But more importantly than that, we become part of some magic that is really changing the world as we know it. So that, I would say, is the biggest appeal for people who want to do, who are inquisitive, or who think that, I want to change the world. Please come be part of it. I'm sure you, with your abilities, you can change the world.
That's a really nice way to put it. And we've talked about, the nuclear science itself, its applications. But I want to just ask one personal question, and especially since you brought up magic. When was the magic for you? Like, what got you interested in nuclear science, in this field? How did you get about it? If you could just give, like, what was your inspiration moment, from your childhood, from adulthood, wherever? Yeah.
I was a 12th standard student, and in the place where I was studying, there was a research scholar who was working on laser holography. And one of the evenings, he somehow saw that, he could show me the lab. And normally 12th standard students are not very easy to allowed access to this, but because I was interested, he showed me the lab. And that was one moment which changed my life, because when you see these things happening in front of you, and you can make a 3D hologram of an object, and it's like what people showed in Mission Impossible, I was able to see it in before 91 on a real laser lab and on a tabletop. And that, I think, is something which I know, that's what I'm saying. That is the magic, and that's the excitement. If you want to be part of it, please do come and see these labs. Most of our labs are open. TIFR Hyderabad. We do a lot of public outreach. Anushila is one of our person who takes care of a lot of these things. We have really cutting-edge labs comparable with the best in the world. And we do cutting-edge science, which we try to compete with the best in the world. And there are opportunities for every citizen of this country to be part of it.
So this question, no, we can go on talking. So I have to restrict it to 1 or 2 minutes. So basically, since I have a chemical engineering background, I cannot say that BRC was my first and only choice. But I applied, and when I got it, my parents were ecstatic, and they said, nothing doing, you are not even seeing any industry or anything, you have to go here. So BRC has a system of training school. So we every year we employ we select very cream, Dila cream from India. About 150 students are taken, around 100 to 150, and then we train them and we attenuate them into nuclear. So they are chemical engineers, they are physics, they are chemistry, they are mechanical, electrical, electronics, computers. All of them come in, and all of us get tuned to what is nuclear, and then we start our this thing. But of course, BRC being BRC, it's so beautiful, and the moment I just walked into for going to that place where I have to give my interview, I decided this is the place I want to be in. Be whatever. The greenery, the beauty of BRC is so, I mean, spectacular. And of course, it comes from, it's a legendary organization. So yes, so these 36 years have passed very nicely, and I have really enjoyed. I've done a lot of R&D and lot of deployment and seen things work in front of my eyes. So really, from my experience, I would tell each child and each person, try your level best and do your best. So many things will happen. Thank you.
Thank you. That was wonderful to hear. There's not many times that we get to hear the, the inspiration behind the scientists who are doing all of this amazing works that's going on in, our institutions here. With that, I think I'd like to end this session. And I mean, there is so much more to talk about this subject, its applications, the various ways that we are using it in everyday life, and potential that it has in the coming years. But hopefully, like, we're in a space called Curiosity Field. Hopefully this sparked your curiosity for you to learn more, to go, read more about it and ask more questions about it. So it's really exciting to have so many people here to listen to this topic. So thank you very much. Is there anything you would like to end with?
Only thanks to Aditi for taking us through this so smoothly and so beautifully, and helping us at least like little adhering to time. Thank you.
I think we're well, ending.
I only second it or third it. No, thank you very much.
Great. Thank you, everyone, and hope you have a good time at the rest of the festival.